summary of the paper From Variational to Deterministic Autoencoders. In the existing VAE framework, an input X is inputted into an encoding network E, which is then mapped to a distribution Q, Z given X. This is sometimes referred to as the posterior distribution. From this distribution, we sample a latent point Z, which is fed into a decoder network and again mapped to a distribution P of X given Z. From this distribution, we can sample a point which we view as the reconstruction of the original input. For a trained VAE, we can view it as being a generative model. By assigning a prior distribution to the latent space, we can then sample from this space of latent point and feed it into the decoder network, again mapping it to this distribution P and sampling from this to produce a new reconstructed point. One issue that sometimes is encountered with the VAE framework is poor generalization in generating samples. This can happen when a point sampled from the prior is outside of the region in which the posterior was trained on. In this case, the sampled latent point, when deconstructed, results in a poor new sampled reconstruction point. The authors suggest a way to overcome this is to remove the stochasticity from the model by making the encoder network and decoder network entirely deterministic. However, in doing so, they lose the ability to sample from a prior and in turn the generating mechanism. To regain this feature, they suggest once the deterministic model has been trained to fit a density estimate to the training points of the latent space. In doing so, you can then sample latent points from this density estimate, and because it's been fit to the samples of the trained latent space, the idea is that it would in turn produce samples that more accurately reflect the posterior distribution, which would in turn lead to better generated sample reconstructions. In considering the original training loss function for the VAE, there are two terms, the reconstruction loss and the KL divergence. First, the reconstruction loss can be problematic in that we must approximate the expectation because we can't find the exact calculation of it. To do this, we must use Monte Carlo methods in which it can produce high variance estimates. To reduce the variance of these estimates, they could take multiple samples for a given generated Z. However, this increases training time. The KL divergence term, if we remove the prior distribution, needs to be eliminated because the model becomes deterministic. The authors proposed a redesigned training loss function composed of three terms: a reconstruction loss having a different form than the one above, a latent space regularization term, and a decoder regularization term. The two latter terms are multiplied by hyperparameters for tuning the model. The reconstruction loss term differs, at first glance, differs quite a bit from the VAE, but in reality they're both incentivizing the same behavior of the loss function. That is, for the reconstructed output to be similar to the original input. In fact, when this uses a Gaussian prior and posterior, this term will actually be involved in this calculation. So yes, they're both incentivizing the same behavior. For the latent space regularization term, we can compare this to the KL divergence term, where it encourages the posterior distribution to match the prior. The prior distribution acts as a regularizer in the trained latent space. In the RAE framework, they mimic this regularization to the latent space in a direct approach using the L2 norm. The third term in their training loss is the decoder regularization term. They proposed three possible implementations to achieve this. One is using L2 regularization on the parameter of the decoder. The The second is a gradient penalty with respect to the original inputs of the decoded encoded deterministic Z. Finally, they also consider removing the decoder regularization term from the loss function and instead applying spectral normalization on the weight matrices of the various decoder layers. To assess the quality of samples produced, they perform empirical analysis. They analyze generating images and generating structured objects. In performing this analysis, they had three major questions that they wanted to answer. One was, are the sample quality and latent space structure in an RAE comparable to that of a VAE's? The second was, for the three different regularization schemes they proposed, they wanted to see how they impact the performance of their RAE. And finally, to what effect their ex-post density estimation, as previously discussed, could be used on VAEs and its variants. Looking first at their image generation experiment, they trained their RAE models on three different datasets: the MNIST, SAFAR 10, and Celeb A. In training these models, they looked at a series of baseline models and variants of their RE framework. They trained each one using the different regularization schemes previously discussed. They also included one without any regularization to the decoder, and one without any regularization to the latent space or the decoder. Among all these models, they had four metrics that they wanted to compare them on. The first was the test sample reconstruction, where the French inception distance is computed between a held-out test sample and the network's output at reconstruction. The second, again, is the French inception distance calculated between a test data and random reconstruction samples generated from a single Gaussian, that is either the prior in the case of the VAEs and WAE, or the density estimate by the RAEs. Similarly, they calculate the French inception distance between test data and random samples generated by fitting a mixture of 10 Gaussians in the latent space. Only in this case, they do it for both the RAEs and the VAEs. This is for them to help address the question of how the ex-post density estimation step affects models other than the RAEs. Finally, they report the midpoint interpolation between random pairs of test data reconstructions. This serves as a measure of smoothness within the latent space. So they published the results for these four metrics across the different models and across the different data sets. And one thing we see is that for the reconstruction of the original inputs, there isn't a huge difference in the reconstruction loss of the VAEs and the RAEs utilizing regularization on the decoder. What is noticeable, though, is for the exposit density estimation when applied to all models. If we compare the performance of the RAE utilizing the regularization schemes on the decoder, the three variants, they outperform all the other models across each of the data sets. And additionally, in the single Gaussian prior used for the VAEs and single Gaussian used for the density estimation for the RAEs, we see that, again, these same three variants outperform the VAEs for the SAFAR 10 and Celeb A datasets. Another noticeable thing is that the sample quality improves when they switch from using the prior to generate samples in the VAEs and the exposit generate density estimation. So this suggests that it could be applied to existing VAE frameworks to improve their sample generation. Heuristically, we can look at the original inputted values seen here, and look at the models reconstructed, and looks fairly similar across all models. So although they differed numerically in the previous slide, just visually you can't see a major difference. But if you turn your attention to the generated samples, one thing to note is that the RAEs utilizing the regularization on the decoder produce noticeably less blurry than those of the VAEs. So just intuitively, from a visual perspective anyway, it seems like the RAE's frameworks in this context is producing superior generated samples. However, this is inconclusive. This is just a small segment of the entire experiment. So now we turn our attention to generating structured objects. In this experiment, they generate mathematical expressions and the structures for molecules. And one thing to note is when generating structured objects is that for generated samples, they have to follow certain structural rules that are defined, or they're considered invalid. So the way they did this was they adapted the same experimental setting as the grammar VAE. And if you want to learn more about this, you can check out this paper listed below. But just as an overview, the way this works is a structured object can be converted into a form of a parse tree. So this is for molecules, but if it was for a mathematical expression, this would be a syntax tree. And the way it works is the branches of these trees correspond with rules for the object structure. And basically, they can traverse these trees and convert the branches corresponding to a rule to one-hot encoded vectors, where the encoding of the one, its index or dimension, corresponds with an ordered set of valid structural rules for these types of objects. So they can project, or they can map these one-hot vectors to a latent space using the stochastic framework of VAEs. And the decoding process is rather involved and a little bit outside of the scope of the discussion of this paper. So the main thing to take away from this is that the grammar VAE could be converted to a grammar RAE simply by removing the stochasticity of which they're mapping these one-hot encoded vectors to a latent space, and instead making it deterministic, then fitting a density estimated to the trained latent points of this model. And that's what they do. So some details about how they evaluate this model is they compare it against the original grammar VAE and a constant variance version of this grammar VAE. So the original used a Gaussian prior, and this also uses a Gaussian prior but with constant variance. They also compare it against another VAE variant called the character VAE, and they report the metric of the percentage of valid samples generated. Additionally, to look at the quality of the samples generated that are valid and invalid, I suppose, they, for the mathematical expressions, they report log 1 plus the mean squared error, where the mean squared error is computed between the generated expression and the true data. And for the molecule setting, they report log p, where p is the water octane partition coefficient. And without turning this into a chemistry presentation, I'll just mention that the water octane partition coefficient can act as a measure of similarity between a general molecule and that of a drug molecule. So a higher quality sample correlates with a higher value of this metric, as opposed to, in this case, a lower value of this metric would correspond with a higher quality sample generated. So looking at this experiment's results for these metrics, one thing to point out is the average scores in the molecule setting. The grammar VAE reports the highest, and because of the water octane coefficient, that means that for the experiment they it produced the best quality generated samples based on this metric. And it ranks second in the mathematical expression generation. But one thing to note is that in both cases, it is producing a higher percentage of valid generations than the original GVAE. So this could be attributed to the density estimation fitting a better distribution to generate quality sampled generations. So in concluding, we'll revisit the questions that the authors originally proposed. First was, are sample quality and latent space structure in RAEs comparable to VAEs? There is empirical evidence to suggest that this is the case. We saw in both cases that they are capable of producing competitive generated samples when compared with VAEs. So this would suggest that the latent space structure is comparable. They wanted to distinguish how the different regularization schemes on the decoders impacted the RAE's performance, and it was inconclusive from their experiment results. There was variation amongst the different datasets. Additionally, they wanted to ask what the effect of the ex post density estimation when applied to VAEs was, and as I pointed out previously, we saw in the image generation that it improved the sample quality of the generated samples. So this suggests that this could be an option to improve existing VAEs frameworks. So some final critiques before I conclude is I believe it showed pretty sufficient evidence that a deterministic autoencoder can learn a latent space of comparable quality with VAEs without forcing a prior. And because of this, it offers a plausible alternative to train a generative model without having to worry about some of the drawbacks associated with forcing a prior. So that being posterior collapse in the case when you have a powerful decoder, or simply high variance estimates in the case of estimating the expectation term in the VAE's training loss. And one final point that is, it's far from conclusive whether RAEs will outperform sample generation of VAEs in all domain settings. There's still much more experimentation needs to be done to answer this. But one future comparison I would like to see is that of the VQ VAEs versus a form of RAE in this setting of generating local samples, because this model has been shown to be a top performer for generating these types of samples. So I would be interested to see how the RAEs perform in this domain. So that concludes my presentation, and I hope you enjoyed it.